Okay, so a very quick reminder of you know a finite group. So, just for completeness, so a set G with a binary operation such that it satisfies associativity. Okay, so X, Y, Z makes sense, right. So, this means that you could group it like this, right, or you could group it like this, right. So, that is just associativity. There is identity. Okay, so that E times X is X times E is X. There is inverse, right. So, for all X in G, there exists an inverse X prime in G such that X prime is X prime X is equal to E. Okay. And a subgroup is a subset which is also a group. Okay. So, let us look at the non-commutative groups that we are interested in. Okay. So, as I already said, one group that we are interested in is the symmetric group Sn, and this is basically the group of all permutations from 1 to n, to the same set. Okay. So, let us consider the set of all permutations. Okay. Now, if I am looking at all permutations from n elements to n elements, what do you think is the group operation? Composition. Good. So, the group operation would be composition. And it is very easy to see that this is not commutative, this group. Okay. So, if I take two permutations and compose them, then the order matters. We can do a sort of simple little example if you want. So, let us say I have 1 to 2, 2 to 1 and 3 to 3. Let us say this is one permutation and the other is 1 to 2, 2 to 3, 3 to 1. Yeah. This is pi 1 and this is pi 2. So, pi 1 composed with pi 2, what is it? Okay, we can do it, but you maybe I do not have to do it. So, I will just claim that pi 1 pi 2 is not the same as pi 2 pi 1. Okay, what is the identity? What is the identity here? Yeah, so every element to itself, right, just the identity permutation. So, that's the identity that is the identity element of the group. Okay, and what's the inverse of a set of a permutation? Sure. So, you can also for every permutation you can invert it. Okay, so that also gives you an inverse. Okay, and yeah, you can also check associative. Okay, so this is one group. All right, now let's so this HSP over this group is connected with the graph isomorphism problem. So, if I could solve HSP over this group, then I could solve the graph isomorphism problem. Okay, let us look at another group. So, this is the dihedral group. So, this is also a group of permutations, but now with a certain structure. So, this is this is the set of automorphisms or self isomorphisms of n cycle graphs. We'll write it down. Okay, so let G again be permutations. That are self isomorphisms of an n cycle graph. So, what does it mean to be a self isomorphism or an automorphism? Basically, if I take the n cycle graph, right, I could apply some permutation which again gives me the n cycle graph. What would be a very trivial permutation? Like what is our n, what is the n cycle graph, right? It's just like this. Right. So, I want those permutations that take this back to itself. Very good. So, cyclic rotation is the simplest example, right? If I just if I just take 1 to 2, 2 to 3 and so on, right, that's something I can do. Another thing I can do is actually reflection. Okay. So, that would be another way to take the graph back to itself. So, good. So, these are the automorphisms. Okay. So, I have n minus 1 non-trivial rotations. Okay, and I have n reflections. So, Dn, this dihedral group, is a subgroup of Sn. Which is generated by a rotation, so just 1 to 2, 2 to 3. And a reflection. So, with that, let's try to dig a little deeper into the hidden subgroup problem. Okay, so a coset of H is denoted by XH. Okay, so clearly, the size of a coset is the same as the size of the subgroup itself, and the cosets of a subgroup will partition G. So, now let F take the domain as the group and the range as colors, right. So, F is H periodic if for each coset XH, F has the same color on all elements. And F gives different colors to different cosets. Okay, so given an oracle for some function which is H periodic, okay, the question is to find H, and this I claim is going to solve or capture the problems that we discussed. So, now can you tell me for Simons what is G and what is H? F2 to the n. Yeah, I guess you are thinking of the generalization. Yeah. Okay, so what is H here? Just 0 and L, right? And what are the cosets? X and X plus L, right? So, H is just generated by L, right? L XOR L will also give you 0, okay. So, if you can find L, you are done. Does everyone see that? Okay, good. So, now what about the next one? So, Bernstein-Vazirani. So, remember here, you had the function as x inner product S mod 2 and you wanted to recover S, right. So, here again G is F2 to the n, okay. H is all x such that x inner product S is 0 mod 2. okay, and there is only one other coset. Which is X such that X inner product S is 1 mod 2. Okay, so now let us look at period finding. Okay, so here H is generated by L, right. So, 0 L, 2 L and so on, and the cosets are translates of H. So, now if I go back to the standard recipe that we have seen, right. So, you will prepare the superposition over all elements in G, that is all the inputs, right. I am going from G to colors, right. Then I will apply the function. Okay, so I will get a random color in the second register, yeah. Then I will measure. Okay, so this sorry, so when I apply the function register, I do not just get one color, I get many colors, right. And then when I measure, I get one random color in the second register, right. At this point, I will apply the QFT, right, and then I will measure and look for clues. So, when I measure repeatedly, I get some bunch of things, and using those clues, I am trying to recover this hidden subgroup, this H. Okay. So, we saw that different subgroups give us solutions to different problems, but it is very intuitive, right. These are all sort of versions of well, exactly the subgroup finding problem. Okay. So, as I said, in the non-commutative group setting, in fact, you have to be more careful in every step, but even the non-commutative Fourier transform etc. will work out. But finally, when we get the clues after applying this recipe, we do not know how to use it. So, this is the reason why our lattice based problems, for instance, are conjectured post quantum secure. So, I really have to emphasize that we do not know if they are or not. So, this is not just about quantum, right. I mean, all of cryptography is based on sort of unproven assumptions, but well, that is the best we can do for now. So, in this case, similarly we do not know if these problems, maybe there is a more clever way of using quantum computers or quantum algorithms to solve even non-commutative HSP even over non-commutative groups. Currently, we do not know how. For the specific example of lattice based problems, which we will see next, it turns out that as far as I understand, the main barrier is that we do not know quantum algorithms that take advantage of the geometry of the problem. So, this is something that we will have to develop an intuition about as we see different problems, but basically at a very high level, I mean the hard problems over lattices, for instance, they are geometric problems, and we do not know how to take advantage of that using quantum algorithms yet. So, we do not know, we will have to see how this works out. Okay. So, I think that is all I wanted to say for this. Yeah, so for non-commutative groups, yeah, let me just leave us with this particular slide. Okay, so for HSP over non-commutative groups, we don't know how to solve it, and that is the source of our belief that lattice problems are going to withstand quantum attacks. Okay. Now, next time onwards we will spend some time studying lattices, lattice problems, and how to build cryptography from them. So, apart from the fact, or the conjecture rather, that lattice problems withstand quantum attacks, there is another very good reason to look at lattices for cryptography. Well, there are multiple. Let me tell you a couple of them. One of them is that the hardness that lattice problems give you is of a better kind. So, you get worst case hardness rather than average case hardness. We will talk about this a little bit. And to me, what is even more interesting and exciting is that the algebraic structure of lattices is so rich that it gives you a lot of cryptography that you did not even know how to do in the pre-quantum regime. So, using things like discrete log factoring and so on, there are a whole host of things that we do not know how to do, and lattices give us a kind of structure that allow us to achieve a lot of really amazing new primitives. We will see if we have time to see at least a little bit of that. So, let us stop here. Thank you.